So as you guys know that for the talk and for the IMAT, you don't have to use the periodic table, or you cannot take with you any periodic table or nothing like to the exam. So what you have to do is to memorize the most important atomic mass and atomic number of each element in the periodic table. Means the alkali metals, the alkaline earth metals, the noble gases, the halogens and halides, the the staircase one, and the non-metals, which are the most top non-metals, and the transition metals, the first column, the first row of the transition metals. Adding to this, you have to know the mercury one, the aluminium, and the platinum, and the lead. So lead, aluminium, platinum, and mercury, and the stair ones, and the other groups, which are the most known groups, and the first row of the transition method. So these are like the most used ones. You don't have to memorize like I have to memorize them super much, and I don't know. It's just like in a way which is basic. Like okay, خلاص. Everyone knows that carbon mass number is 12. Nitrogen 14, oxygen 16. So like in this way, you know, like these base things, you should know them for the IMAT. So this for the periodic table. So let's speak about the periodic table sometime. So let's say here we have the periodic table. We have the alkaline metals, the alkaline earth metals. Okay, the girl entered. Let me just make sure. Okay, Ganesh, your name is Zilan here. Okay. Okay, welcome. Welcome in the class. And perfect. Everyone now is with us in the class. So here's the periodic table. We have the alkali metals, the alkaline earth metals, the second group. Here we're gonna have the non-metals. And we'll have here the noble gases, the halogens and halides. And what else? We're gonna have here the stair one. Here are the transition metals. Okay? Let's say that this is the periodic table. So what we should know for the periodic table, for the IMAT, what you should, what are the characteristics that you should know? We have first, I want you guys. Okay. Welcome, Ali. So guys, I want you to help me with the characteristics just to make sure that you guys know about these characteristics and already studied chemistry before. So one, electronegativity. Two, atomic radius. Three, metallic character, which is just for the metals. This character is just for metals. Character. Four, ionization energy. And five, electron affinity. So these are the main five characters that you will be asked about them in the IMAT, which are the electronegativity, the atomic radius, the metallic character, the ionization energy, or we can say the primary or the first ionization energy, and the electron affinity. What each of these characters is going to help us to be able to identify this periodic table and to understand the concept of the periodic table. So, the electronegativity is the ability of this atom to be able, no, to be able to attract an electron. So, who is the most or the highest electronegativity in the whole periodic table? It's fluorine. So, fluorine is the highest electronegativity. And the lowest electronegativity in the periodic table is here, cesium. Atomic radius. The atomic radius is the radius between the nucleus of an atom with, or between the one nucleus of an atom and the another nucleus of the atom. So also, the metallic character is just the character of the just a character that characterizes the metals, and it's the level of the reactivity of the metals, or how much is this kind of metal reactive. Ionization energy. So ionization energy is the ability of this atom to lose an electron, to take from the energy shell an electron outside, or to excite an electron outside this atom. So, so there is a kind of a relation between the ionization energy and the atomic radius. We're gonna speak about it. And of course, if we increase the protons or we increase the number, the atomic number, the size of the proton is gonna be smaller. And if we increase the shells of around this nucleus, also the size is gonna be higher. So high. So we're gonna speak about the ionization energy. Okay, so high protons equals to high size. High shells equals to high size, not high size, low size. Okay. So when we have a smaller size of an atom, let's say we have lithium. So lithium will have the 3 electrons. This is the lithium. It will have 1, 2 here, and 1 outside. The atomic radius is this much, from the nucleus, the center of nucleus to here. So if you see that lithium is like this, and let's say we have, other than lithium, we're gonna have hydrogen, which will have only 1 in the first shell. So if you see that the atomic radius of hydrogen is much smaller than lithium, and the bonds, or the how much this atom is tight and strong, hydrogen is more strong and tight than lithium. Why? Because the more you go far from the nucleus, the more the electrons are far from the nucleus, the bigger the atom is, and the no. So 1 second, guys. Yeah. So okay, let me draw it in a better way. Okay, and let's say we have another atom here. Okay. So let's say, guys, that we have 2 atoms, one here and one here. One, let's name them 1 and 2. Okay. Here we have electrons all over the shells. And here we also have electrons all over the shell. Now, the more we have electrons, okay, and the more we have shells, of course, we're going to have bigger size. This is normal. Why? Because more shells will increase the size of the atomic radius, and will increase the size of the atom because you're going far, okay, from the nucleus. Now, when you're gonna have high protons, let's say here we have so much protons inside the nucleus. So the size of this atom will diminish. It will be less because the atomic radius will be so, the atom will be so tight to the protons, and the atomic radius will be less. So, and the size will be also smaller. So what I was trying to say is more protons, less size, more shells or more electrons, high size. Okay, so electron affinity. So now we were speaking about the atomic radius and the ionization energy. Okay, and the electron affinity is the energy released when electrons gained by an atom. So when any atom gain this electron, the energy which is released from this electron, it will be the electron affinity. And here we're gonna have high proton. So for the electron affinity, let me try to do this. 1 second. It's not deleting. It doesn't want to delete. So let me try to write it in a better way. Everything. So the characteristics of the periodic table. Ionization energy. High protons. Low size. High shells. High size. Electron affinity. We're gonna have high protons, high electron affinity, low size, high electron affinity. Let's say we have an atom, and in this atom we're gonna have an electron, okay? And this atom wants to gain an electron from the surrounding, okay? So this atom gained this electron to complete the octet, let's say by any bond, by any kind of bond, whatever. So by gaining this electron and bringing it to the valence shell of this atom, so there is a kind of energy that will be released by this atom, which is called the electron affinity. When it gains an electron, it releases an energy called the electron affinity. Okay? And the metallic character is the level of reactivity of metals. So metallic character is how much this metal that I have here is reactive. So level of reactivity of a metal, and this character is only for metals. So okay, and we spoke ionization energy, electron affinity, metallic character, atomic radius, and electronegativity. Okay, so what should we know about the periodic table? This is the periodic table, let's say. Okay. So when we go hide the groups of the periodic table, so we're gonna have here the characters. Number one, let's speak about the electronegativity. We're gonna draw the electronegativity either in this way or in this way. Electronegativity increases from down up of the periodic table. So here it increases. Or you can draw it in this way on the periodic table and say that it increases going from the left to the right or from up to down it decreases. So increases here, decreases here. So you can kind of screenshot this to go to the second one. So let's say who have more electronegativity. Is it sodium or carbon? It's carbon. Why? Because sodium is here and carbon is here. It's increasing. Who has more electronegativity? Let's say zinc or nitrogen. Of course, it's nitrogen because it's increasing all over the way here. So from zinc going up to nitrogen. Okay. Usually, you can take it as a rule that non-metals are usually more electronegative than all metals. And hydrogen is one of the most electronegative metals that we have. Okay. So let's go for okay. So let's write here the second one, which is ionization energy and the electron affinity. Okay, so we can draw it in this way. So the electron affinity and the ionization energy, they increase up and they increase. So they increase here and they increase going from left to right. Okay. However, we have the atomic radius and the metallic character. So they increase in the opposite direction and they increase down the group. Okay. So now I want, before I continue, I saw a question in the IMAT. I want to just ask it one moment, like in the booklet. Okay. So consider the following list of particles. Okay. Molecules, ions, single atoms. So we're gonna have molecules, ions, and single atoms. Which one of the following objects correctly describes the particles that are present in an aqueous solution of sodium chloride? If we have an aqueous solution of sodium chloride, do we have molecules inside it, ions, or single atoms, or all together, or which ones of them? Just see if anyone Gonna answer. No, not all together. So, Humira, we're gonna have an aqueous solution of sodium chloride, NaCl. This aqueous solution of NaCl, okay, it will end up with ions, molecules, atoms, or three of them together, or which ones? Bravo, ions, of course. Bravo, molecules, Sayed. Bravo, Sayed. And do we have single atoms or no? Do we have single atoms or no? No, excellent, excellent, Sayed. So we won't have single atoms, okay? Because sodium chloride, they are bonded by ionic bonds. So of course, molecules and ions without single atoms, there is charges here. Okay. So let's see. We spoke about these. So as we said that the ionization energy and the electron affinity increase up the group and increase from left to right. And the metallic character and the atomic radius, they are in the opposite direction. Just try to memorize this and the electronegativity and everything will be okay. Now, I want to write some definitions. What time is it now? Okay. So, discuss the concept of reaction yield, okay, in light of the law of conservation of mass. So, does anyone know what does the reaction yield mean? What is the formula of the reaction yield? So, the reaction yield formula is mass obtained over mass theoretical. If they ask us about the reaction yield percentage, we're gonna multiply this fraction by 100. And they said according to the conservation of mass. This means that we're gonna use mass and not number of moles. If they said give me the relation between the reaction yield and the number of moles in this compound, we're gonna use instead of mass number of moles. So it just depends on the question. Another definition. So this is the reaction yield. Another thing. Define atomic number, mass number, and atomic mass unit. So atomic number, or Z, is the number of atomic number, or Z, is the number of what? Protons. Protons, perfect. No, it's just protons. Z is just the number of protons, guys. Mass number A is the sum of the number of protons and the number of mass number A is the sum of the number of protons and the number of A equals to Z plus N. This is the mass number. This is the atomic number or number of protons. And this is the neutrons. This is the formula. Okay. Atomic mass unit is, so the atomic mass unit, or international unit is the AMU or the Dalton. Yeah. These are kind of small definitions you should know. And of course, what kind of particle inside an atom gives the identity of this element? Is it the number of neutrons, the atomic number, the atomic mass, the mass number? What kind of number inside this element gives it its identity? Bravo, it's Z, the atomic number, the number of protons. Why? Bravo. Because every single element in the periodic table has a different atomic number. However, they might have the same mass number. Why? Because here we're gonna go for the concept of isotopes. So let's think about isotopes. Isotopes are the same. Why is the handwriting like this? Elements that have same number of protons, which is Z, but different number of neutrons, or different mass number A. Of course, since the formula is A equals to Z plus N, if the number of neutrons is changed, A gonna change. If the number of neutrons is constant, A gonna be constant. Okay? So another thing is that let's say H1, H2, these are isotopes. They both of them are hydrogen. However, and both of them have only one proton. However, each one of them has a different number of neutrons. This one has A equals to Z plus N, 1 equals to 1 plus N equals to 0. Okay. And this one will be N equals to 1, so different number of neutrons. Okay. Okay. Okay, what is the relative atomic mass? So they might ask you about the relative atomic mass. It is 1 over 12 of the mass of the isotope 12 of carbon C612 12M C612 equals 12,000 AMU, and it is the mass of an element, since it's relative, so one in respect to the other and relative to the other, an element with respect to another. A formula you should know is 1 AMU equals 1.66 times 10 power minus 24 grams. So the relative atomic mass is 1 over 12 of the mass of the isotope 12 of carbon. And you should know this. Okay, and it is the mass of an element with respect to another since its relative atomic mass. And you should also know this. Okay. Twelve thousand AMU is the mass or the mass unit of the carbon 12. If you see here, if you try to calculate, by the way, if you try to calculate in physics, not in chemistry, the mass of this carbon, this isotope here we have, you will find out that this exact number will be out as 12,000 AMU. Okay? And it won't be the exact one. It might be 11.99 thousand, but at the end, it's almost the same atomic mass. So the mass number, I mean. So it's just a kind of mm, like a kind of representation for the mass number depending on the atomic mass unit. So let's say like here 12, we just like, you should always multiply by 1,000, the atomic mass unit, from the mass number. This is A. A is the mass number. It's not A, it's A times 1,000. There is a difference between the mass number and the atomic mass. There is a difference. The atomic mass is this. Atomic mass is this. Mass number is this. Okay. Now, medial atomic mass. So, medial is the absolute atomic mass or real mass measured in grams. And now I just wrote the formula of how to measure from AMU to grams, how to transform yani. So we can use that formula, which is equal to the relative mass the one that we just finished now, times 1.66 times 10 power minus 24, and will give us this number in grams. Let's say the relative mass is 12,000. The medial mass is 12,000 times 1.6 because it was 12,000 AMU. This is the relative mass, okay? If you multiply this relative mass by 1.66 times 10 power minus 24, it will give us the number in grams. This is the medial mass, M, the small m. Okay? Is everything clear? How to calculate mass number? Or how to calculate mass? I'm not understanding. What do you mean by this, Sayed? Want to just make sure what's your question. Mass from AMU. You mean like how to calculate this mass? It goes back to physics, I guess. There is a formula that says number of moles n equals to time over the whole time. But you don't have to calculate the AMU because how will it come on the IMAT? They will tell you, okay, C. They will be like, okay, C 612. And they will ask you about the medial mass. So here you already have the relative mass, which is 12. You just add 1,000. It will end up with the unit, AMU. And then you multiply it and you end up with the grams. So you don't have to calculate it. You just have to use the mass number and multiply it by 1,000. That's all. Not understanding. Yeah, I told you the trick of calculation, the way of calculating it. You just go to the mass number, you multiply it by 1,000. Here you're gonna have the atomic mass unit. And then you multiply this atomic mass unit by this number, you're gonna end up with the median mass. Okay, so is it recording? Perfect. So now we're gonna speak about the mole. In international system, it is defined by the quantity of a substance or molecule or atom which contains same number of particles in 12 grams of C612. I will get the number. Okay. I just want to tell you something, guys, before we continue. Yeah, exactly. Exactly, 100%. Okay. So, guys, these definitions that I'm giving now. So I have the book of the University of an Italian university. I'm using the definition from the Italian university books, like the books that they teach in universities here in Italy. So these definitions are the same definitions that Italy itself or the Ministry of Education in Italy produced. So that's why I'm giving the definitions in like details, because the IMAT, they ask for the smallest detail in the definition. So according to the Italian Ministry of Education, they use these exact definitions that I'm giving and they work the IMAT on. Okay, so try to memorize the definitions like in by word. Okay, because this book is an Italian book in the university inside Italy. They teach they teach from this book in the first year chemistry for general chemistry, for the general chemistry subject in the first year. Okay, so try to memorize this definitions by word, like memorize them by heart. So the mole is in SI. It is defined by the quantity of a substance or a molecule or even an atom which contains same number of particles in 12 grams of carbon isotope 12. Okay, it's the number of moles that we know, but I'm just giving the definitions so in case you needed them. The molar mass, the mass of 1 mole of a specific substance. Okay, and the molar mass equals N equals M over N, the mass over the number of moles. However, the molecular mass it's the same exact it's the same as the molar mass, but the unit, the only thing that is different is that the molar mass is the unit of the molar mass is gram per mole, and the unit of the molecular mass is AMU. So here the mass of the element over the number of moles of the element. Okay. Okay, so these are the definitions that you must know for the IMAT, or basic definitions of chemistry you must know for the IMAT. Perfect. So everything is okay? Okay. Now we're going to speak about now we're going to speak about the atomic structure. So the atomic structure. Define the possible values of quantum numbers and LMS and indicate the properties that they represent. So we have four quantum numbers, which are the N, the L, the M, and the S, the MS. Okay. MS. Okay, so this is the magnetic one. Number one, they asked us to give the values of each one. So you should memorize that. We have four values of quantum numbers in this atomic structure, in this atom. So the values of N goes between 1, 2, 3, 4, 5, up to infinity. Always positive. The value of L equals 0, 1, 2, 3, up to n minus 1. The value of m equals plus L, L minus 1, plus L minus 2, going up to 0, then continuing, minus L minus 2, minus L minus 1, minus L. Okay? And the ms value, which is the magnetic one, it's either half or minus half. These four memorizing. Okay? So if you want, I can draw a chart for you and explain for you. And now I'm gonna, of course, explain everything written. So first, I want you to write these numbers. Write this on your CV, on your copybook, and then I will explain each one and why am I writing these values and everything about them. Okay? Okay. So what are these quantum numbers? You can write quantum numbers. So these quantum numbers, n. So n, by definition, it is the principal quantum number. Okay. N is the relation with the dimensions and the energy of the orbital. So n is the relation of the dimensions and the energy of the orbitals. Okay. The greater n, the higher the probability of finding the electron at a greater distance from the nucleus. So if we have high n, high principal quantum number, we're gonna have a high distance from the nucleus. And we're gonna have a higher energy. And the moment you have a higher energy, of course, it will be, we're gonna have a very high probability of this electron to be super distanced from the nucleus. So high n equals more orbitals or higher orbital. Okay, high n equals low amount of energy between the orbitals. So high n, high distance from the nucleus, we're gonna have a high energy in the orbital. However, we're gonna have a low energy between the two orbitals together. High n, high orbitals. Okay, so this you should know about n. Does anyone have any question? I think it's something new on you guys, or I don't know, some of you already studied this concept. I just want to make sure everyone is okay with it. Before this one, it was not in the it's still not in the I would say the syllabus, and but so much questions are coming in the IMAT out about this. And plus, there were 3 questions this year in the TORC exam, the medicine exam, in Italian language. They didn't say that this is in the syllabus, which is the quantum numbers, but it came 3 questions. So we should always be on the safe side and study all the courses possible. Okay? Because you might think it won't come, but it might come. Like last year, they said, not last year, 2022, they said in physics, the rotation will never come. And they brought 3 questions rotation. So no one knows what happens to their minds. That's why. Okay. Okay, so if n equals 1, let's say, since we said n equals 1, n equals 2, n equals 3, going up to infinity. So let's say n equals 1. First one from the nucleus. Okay. If n equals 2, second from the nucleus, n equals 3, it will be the third of from the nucleus, and we continue and so on. And this n, which is the energy, and the dimension orbital, this n, it corresponds to bar energy level. So if you remember, or I don't know if you studied about the bar energy level, he used to speak about it when he spoke about the energy level, which defines the energy of the orbital and the dimension of the orbital. He meant by n, by the first one. Okay. So these all of the things that you should know about n. It can start from 1 ending into infinity as value, and it corresponds to bar energy level. If n equals to 1 means it's the first energy from the nucleus. N equals to 2, second from the nucleus. It is the shell number basically. Yeah, it's basically the like the number. Okay, so it defines the energy of the orbitals, which is n. Okay, so we spoke about n. Let's go for L. L. It is the secondary quantum number it influences the shape or the form of the region of the space equipped from the electron and the degeneration of the orbitals and the degenerations orbital. So it speaks about it influences the shape or the form of the region of the space equipped from the electron and the degenerations of the orbital. L can be equals to 0. When L equals to 0 means here we have how many orbitals? We're gonna have only one orbital. And we're gonna have degeneration 3. If L equals to 2, if L equals to 1, 2 orbitals. Let's say L equals to 1, 2 orbitals. Degeneration. L equals to 2, 3 orbitals. Yeah, this. And the degeneration is 5. These you should know. So if N equals to 0, here we're gonna have only one orbital. The degeneration number is 3. If L equals to 2, we're gonna have 3 orbitals and the degeneration number is 5. So it just kind of speaks about the shape or the form of the orbital that you have. Okay. So if I think in the electron configuration, since all of you studied for the IMAT, I think in the electron configuration, all of you know the concept of SPDF. If anyone don't know about this concept, tell me so I know. Like so I know how to explain them before I continue. Okay. So okay. So basically, SPDF are these orbitals that we fill in the electron cloud, or that the electrons fill in the electron cloud. And when they fill these electrons, of course, they have to fill a limited number of electrons in the electron cloud, or else they cannot be fitting in one orbital altogether. Or let's say in one. Oh, guys, I really have to charge my phone because I'm using the 4G. So let me just charge it. Put on charger. Okay. Perfect. So let's say, so from where the concept of SPDF came. Now, there is something that you should know. Yeah, I'm sorry, guys. Someone. Okay, let me just make sure. Okay. Okay, perfect. So, guys, there's three people not with us now in the meeting, and I really want you to focus on studying. Like, do not buy the recordings above your head. You already have just not so much time, little time from now, like distancing you from the exam. So try not to pile the recording up. Try to enter the meeting like and how we say, try to ask questions, understand, is better than piling them up and not understanding nothing later. Or just not studying them and going to the exam or waiting for the last minute before the exam. It's not good. Okay. So, Sayed, what do you mean by degeneration? You mean degeneration in the L orbital? It's like degeneration. It's like the existence of more than one orbital in the same energy level. Like how we say, let's say we have the energy levels. Before, when we used to be young, they used to teach us that we have energy levels which are K, L, M, N. Okay, so K, L, M, N. These used to be the energy levels. When we have more than one orbital here inside this level, this is called the degeneration. Now, when we say 3 degeneration, mean we have 3. When we say we have 5, mean we have 5. This is what I mean. It depends, of course, on the number of L, of quantum number. Exactly, M equals 2 L plus 1. We're gonna reach M. Just let's finish here. Okay. So basically, we were speaking about the SPDF. So, who studied about the electron configuration know that we have the orbitals which are the SPDF. S orbital can only hold 2 electrons, P can hold only 6, D 10, and F 14. Okay. Okay, K and MN, this one. These are the main orbitals. K can hold only 2, L can hold only 8, M can hold, no, 6 or 5. I don't remember. This used to be old, but like M that was 8 and N is the rest. But for the IMAT, you should just focus on this. Okay. Okay. So, let's speak about the SPDF1 according to L. So let's say we have L. Let's draw this chart. L and the symbol. F can be 0, can be 1, can be 2, can be 3. Okay. So if L equals to 0, we're gonna have only one. As we said, we're gonna have only one orbital, and we're gonna have 3 degenerations. So what is the main orbital that we have is S. So we're gonna have only one S. If L equals to 1, we're gonna have P. If L equals to 2, we're gonna have D. If L equals to 3, we're gonna have F. Okay? S usually is a spherical structure. When I first spoke about the definition of L, we said that it works on the shape or the form of the orbital, or it describes the shape or the form, and it also describes the degenerations and how much degenerations do we have in the orbital. So F is this spherical. P, the shape of P is 2 balloons tied at knots. Like this. D is 4 balloons tied at knots. And F is 8 balloons tied at knots. Let's say D, let me try to draw it. Okay. So, and here we're gonna have an 8 in the F. First principle, L equals to 0. So, when L equals to 0, we said we're gonna have only S, so 1S. Second principle, let's say L equals to 0 and 1. We're gonna have 2S, 2P. If L equals 0, 1, 2, we're gonna have 3S, 3P, 3D, because we said at 2 we're gonna have a D. We said at 1 we're gonna have a P. We said at 0 we're gonna have an S. 0 we're gonna have an S. 1 we're gonna have a P. 0 we're gonna have an S. This is the first principle. Here is the second principle. Here is the third principle. Here is the fourth principle. And first principle is this. And this basically is in which row this element is. Okay, so it depends on the row, or you can say the period. This coefficient behind S, or the principle, we can say. For L equals to 0, 1, 2, 3. Okay, here we're gonna have 4S, 4P, 4D, and 4F. Why 4F? Because at 3 we're gonna have an F. If you remember when we just drew the chart, we said 0, 1, 2, 3, S, P, D, F. At S we're gonna have a 0. At P we're gonna have a 1. At D we're gonna have a 2. At F we're gonna have a 3. Okay, and all of the rest have 4 or more. All of the rest. But we're mainly focused on these 4 principles. Has 4 or more. Okay, so everything is clear. Yeah, they are odd numbers. SPTF, they are odd numbers. You're speaking about the degenerations. It's not S has 1 degeneration, P has 3, and D has 5. Not in this way. Because the degenerations does not depend on listen, it's if we have S, we have 3 degenerations. If we have D, it's not calculated, it's memorized the degenerations. There is no calculation of degeneration. Okay, let me just make sure of the number. You don't have to memorize the degenerations, but if you want additional information, you can, because it's not asked for the IMAT, the degenerations. So degenerations. Okay, yeah, you wrote the numbers. Okay, try to know that they are odd numbers. That's all I studied, to be honest. For the when I was studying the IMAT, I just studied that the generations are odd numbers. All of the odd numbers after each others. This is how I studied them. Like 1, 3, 5, 7 in this way. I continued. So yeah, as you wrote them, try to study them in this way. Can you also please explain the octet rule? When do we have to place 8 electrons and the shell can occupy more? Okay, the octet rule. So let's say you have the carbon atom. It will have a 4 in its valence shell. So here it needs to continue the octet. So it will try to bond with another, let's say two atoms or three other elements, or one another carbon, to be able to continue the octet by adding 4 to it. Why? Because we have 4, the octet is 8, so it has to continue the 8 electrons in the shell. So it kind of makes a bond with another electron to be able to share electrons. So both of them will continue the octet. Okay, when do we have to place 8 electrons? What do you mean by you have to place 8 electrons? You have to continue the valence electrons to reach 8. KLM shells. Yeah, these shells, exactly these shells. You have to try to make these shells at the end all full. Have 8 at the end. Okay. So, okay, so we spoke about L, and now let's speak about the last one, which is M. So M, write the definition, guys, because I have to leave so soon. I mean, like, yeah, exactly, 100%. Some of them can, do we have, no, you don't use the octet rule. Some of them can hold 18 electrons. You cannot use the octet rule in this. When do we have to use the octet rule? The octet rule is to continue the two, to continue the octet between the two, is you have to find a way to bond them together to end up with the octet. Some of them will have higher, means means that they have more electrons in their energy levels. So you should not continue the octet in them. Okay, so MP is the magnetic quantum number. Describes the orientation of orbitals in space relative to another one. Orbital relative to another one, or another orbital. So MP equals 2L plus 1. So let's say we have the first one, 3, 5, 7. These are the generations. So of course you're gonna have the S, the P, the D, the F. So L equals to 0. Here L equals to 1, L equals to 2, L equals to 3. So here the value of M is 0. Here the value of M is minus 1, 0. Why? Because to L plus 1. So 2 times 0 equals to 0. Yeah, I guess it must be 1. So 2 times 1, it's 2. 2 plus 1 is 2L. 2L plus 1 equals to MP. Yeah, exactly. So minus 1, 0. Here we're going to speak about the value. And so 0, minus 1, 0. And 1. Here minus 2, minus 1, 0, 1, 2. And here minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay. So as we said, so MP equals to L plus 1. If you do the calculation, you're going to end up with the degenerations or with these values of MP. What is the definition of the magnetic quantum number MP? It is the orientation of the orbitals in the space relative to another orbital. How is this orbital is oriented according to the another one? Okay. And the last one is the spin quantum number. So experimental information described completely that the electron is like a sphere. It orbits around its own self, generating a magnetic field, which is a small one, with two poles, south and north, from S to N. It's kind of small magnet because it's a kind of orientation around the electron itself. The rotation of an electron is quantized or well defined. So the thing that you should know here is the orientation of the electron itself around itself is quantized or well defined, in which only two orientations of this magnetic field of this small magnet with respect to the external magnetic field will happen. So it is only possible for only two movements of the spin around its own self in clockwise and anti-clockwise direction. So this electron is going from south to north, and then from north to south, in the direction from S to N. Okay, so it is kind of orienting in clockwise and anti-clockwise, and then clockwise and then anti-clockwise, reaching two numbers, which is the ms equals half and the ms equals minus half. Why one is against the other having the same value? Because one of them is clockwise, one of them is in anti-clockwise direction. It's a kind of magnetic orientation of the electron around itself. This is the spin magnetic quantum number. Okay. So let's say, okay, so now we're done with the quantum numbers. So let's make a small summary. The quantum numbers are NLMN, NN, and NMMS. Okay, so N is the one that describes the energy and the dimensions. L describes the form, the shape, and the degenerations. M describes the orientation, and MS describes the orientation of the electron around itself. Okay. Okay. So Sayed was asking me about the valence electrons, when it will continue the octet, when not. So usually the electrons, when you see like an atom that already have 8 valence electrons in the like in the last energy level, This means that already have the octet, so it does not have to continue any octet. It will have to gain to bond with another electron normally without even following the octet rule. However, if we have an atom that does not have the valence electron, which is 8, let's say helium, hydrogen, lithium, beryllium, boron, these ones, they need to continue the octet because their valence electrons are not are like 7, 6, 4, 1, so they have to continue the octet. However, the octet rule is not followed by all of them because some of them, they have more than 8 valence electrons in their energy level, like sulfur, like phosphorus, like chlorine. These, they need, they exceed the octet. They don't have to continue. And yeah, so this is the only explanation for this. So it just depends. If it already have a valence electron, which is like more than 8 valence electrons, means it already has the octet. So let's do something. If at no number is 56, then how will be divided between the K and MS shell? Um, okay, so as we said before, the rest will go for N. Second, they will be divided in a way to end up at the end higher than the octet. When it's higher than the octet, does not have to continue the octet in any way. It's already reactive. And they try to fill the K by 2, the L by 6, the M by 8. Everything left, they give it to the N. Okay. Of course, K won't be able to handle more than 2. So everything left will be given to the N. Okay. Now, um, okay, now I will speak about something, small thing, and we're gonna end the lesson because I have to do something important. So yesterday we gave 30 more minutes. We're gonna use this 30 of yesterday to add them to the, like, instead of the continuing the 30 more minutes of the lesson, we already did them yesterday. Because there's something important, I have to go now and do it. So I want to just give a small note before I go. Perfect. Perfect. Okay, so guys, I want to explain something. So since we spoke about the L and we said that the L shows the form or the shape of this orbital, what do you think the shape of the S orbital is? The S orbital shape is spherical. Excellent. So it is spherical. We have here 1s, 2s, 3s. Gets bigger with the number. So this is the S1, the S orbital. The P orbital, as we said, it's two balloons tied to an up. So let's say Px looks like this on the axis. So Pxy, because these two balloons are aligned on the x-axis. So that's why it's Px. Let's say Py, so we're gonna have x, y, z on the axis. The Py, I mean Pz, looks like this. So here the plus, here the minus. And okay, so and the Py is one. Two balloons tied to a knot, and here the plus and here the minus. Okay, this is the P1. The D, as we said, it's 4, so it looks like this. You should not know the shapes for the IMAT, but I'm trying to make you just imagine how they look like in space. It's kind of 3D shape. This is D, X, Y, and the F, you're not asked about it, but it's 8, it's not 4. It will be 4 from the showing side and 4 from the hidden side, which is behind them. This how it shows in space. You're not asked about these figures. You just have to know as a shape, like as an overall shape, how they look like. Okay, so why the meeting? Okay, let me just stop recording.